Just 1 second. Okay.
Okay, I'm Vivek. I'm a scientist, senior scientist from ENCAR. Work with instrumentation, mainly with in this project with hyper cloud radar called HCR and HSRL. It's a LiDAR. These instruments are getting deployed in CSET program. I have a picture of HCR on the screen. Shows the HCR is a pod-based system. It's mounted under a G5 wing, as we see here. And this pod is about 4 meters in length, about half a meter in diameter. Within that, we have the whole radar, which is a W-band 94 gigahertz 3 millimeter wavelength radar is put in place in a pressurized scan. As we see the layout of the system, we have a lens antenna. It's about 0.7 degree beam width. It's a blue color here. The transmitter and data systems all put in the pod. This is scannable if necessary. We can scan in the cross-track scanning. And we have all of the attitude corrections which are mounted here so that we can compensate for any aircraft motions and altitude changes. That way we can get excellent measurements of locations. That helps us to compensate for aircraft motions in velocity measurements using the radar. And this radar is a Doppler radar, plus it can measure both co and a cross-pole measurement, that basically the reflectivity backscatter power and the cross-pole measurement, plus the Doppler and spectrum width. With this radar being deployed here, we have also LiDAR. The LiDAR is a high spectral resolution LiDAR. It's a green light. As we see, this LiDAR is the cabin-based system, which is within the cabin of the G5, and that's the LiDAR telescope, the LiDAR unit here. And that unit, as you open here, it's a green light, as we see here. And this green light telescope, it's again the same range as the radar. It's 15 kilometer range with a resolution of 7.5 meter along the beam. It can measure the aerosol and the cloud particles. And it's about is a 40 centimeter is the beam width of the LiDAR. Of course, it doesn't expand. It's kind of like a beam, which basically it goes as a very sharp 40 centimeter beam. And these instruments are flown on G5 to get measurements of aerosol clouds in this project. Now, an example of a LiDAR data set here, this shows 12th July 2015 is taken. This is height above the ocean surface, goes up to 6 kilometers in this case. This is whole thing's about half an hour. As we see the very nice features of aerosol features here, and there are boundary layer aerosols. And again, we got this very dark red color corresponds to strong backscatter from cloud particles. The scales are shown here. It's measured in meter per stadian. It's equivalent of radar backscatter. The radar may not be able to see any of the aerosol characteristics. You can see the cloud characteristics here. The next picture shows the corresponding image to this data set on 12th July, where we have measurements of radar taken around the cloud features. As we see, it shows much deeper. You can see all through the cloud in the radar images, and it's about in this case about 6 kilofeet height, and we got a very strong DBZ values where the drizzle particles and cloud particles with a minus 22 or minus 25 DBZ echoes here. And these are the measurements we take as the aircraft flies over the ocean. And the next image shows corresponding Doppler velocity. The strong velocity corresponds to the downdraft, corresponds to bigger particle as it's raining down. And there are good features in this one as we go through this. And the next image shows a spectrum width. Spectrum width, the spread in Doppler velocity, again gives you an idea about how particles are small and big, how broad they are. And you can say low spectrum width, larger spectrum width. PIs in this project, particularly from Miami, Florida, Bruce Albright is planning taking these measurements of detailed measurements of Doppler velocities as we show here. From there infer the droplet size distribution, onset of droplet, drizzle versus cloud particles. And these are very critical measurements for the PIs in this project. The next sequence of image shows even shallower cloud. This case you can see the contiguous features of very flat-topped clouds here. Again, the DBZ changes very small, large values. In this case, the difference is aircraft is flying very close to the ocean surface looking up. In the previous case, it was looking down, taking the measurement. This aircraft is able to fly close to the ocean surface, take the measurement as it looks up. And this gives a very good resolution and also high sensitivity images, like even up to minus 35 dBz echoes, as we see here. Very light echoes. These are micron sized particles, as we see in the cloud droplets. And again, we got also big drops, drizzle drops. Since this W band radar has a great sensitivity to measure the small to large droplets. Now the corresponding measurements of a Doppler velocity here shows that even there are values which are much smaller, minus 2 negative velocities. Basically, that means it's approaching the fall velocities here. Most of them are basically raining out in this case. This shows basically a cross-pole measurement, being the measurement being close to the radar. You can see cross-pole measurements are saying that it's all water drops in this case, minus 30 dBz, minus 25 dBz echo. There is no ice particles in this, are all warm clouds, and that kind of emphasizes how big the particles are, the spherical particles. And so we have the core and cross-pole measurement. Corresponding to that, we have again a spectrum width, again showing the similar feature here. The red color here, because of poor signal to noise ratio, is not actually, it shall be corrected later in the project, but mostly we could see spectrum widths are close to a small value less than half a meter per second. That shows again particles are small, and it's a low precipitation system. And this is a corresponding HSRL images showing how strong the cloud liquid layers are. It doesn't show all the way up because HSRL get extinguished as it sees the cloud particles. It doesn't see anything above the cloud because it's much stronger optical depth here, greater than optical depth 2. HSRL get extinguished here. But we could see nice feature below the cloud layer, the aerosols, and again small cloud particles in this case, that's kind of shown. And so in this project, given this LiDAR and the radar, it gives a comprehensive picture of the radar and LiDAR comprehensive pictures of aerosol and the clouds. In the clouds, you can look at it, cloud particles and drizzle drops. And this kind of a very comprehensive first-time deployment for the scientist from NCAR. We are trying to learn from the PIs in the field so that we can improve the data quality and what kind of things we need to put scientific products. This is a collaborative project because these instruments are developed past 4 or 5 years in NCAR, but it's the first time getting deployed, getting a feedback from the PIs, see how this could be applied to the science while looking at it in a cloud system evaluation in trade